Now in this section we consider collisions. By a collision we mean a situation in which two objects strike one another. And in collisions we consider the net external force is either zero or negligibly small. For example, if two train cars roll on a level track and hit one another, that is a collision. In this case, the net external force, that means the weight downward plus the normal force exerted by the tracks upward, is zero. And as a result, we can say that the momentum of the two-car system is conserved. Momentum of a system is conserved does not mean that the system's kinetic energy is conserved. In fact, most of systems' kinetic energy is converted to other forms of energy during a collision. Therefore, in general, collisions are categorized according to what happens to the kinetic energy of the system. And there are two possibilities, inelastic and elastic collisions. So after the collision, if the final kinetic energy is equal to the initial kinetic energy, then we say that the collision is elastic. And if the initial and final kinetic energies are not equal, then we call the collision is inelastic. First, let's talk about inelastic collisions, where the kinetic energies are not conserved, but the momentum is conserved as long as there is no external force acting on the system. Now, there is a special case in inelastic collision, where the objects stick together after the collision. In those types of collisions, we say that the collision is completely inelastic. Now let's see inelastic collisions in one dimension. Consider a system consisting of two train cars of mass m1 and mass m2 on a smooth level track. And when the car collides, the coupling mechanism latches, causing the cars to stick together and move as a one unit. Now, what is the speed of the cars after the collision? So, to answer this question, we begin by noting that the system has zero net external force acting on it. Therefore, its momentum is conserved. So, which means the initial momentum is equal to the final momentum. And the initial momentum of the cars are mass of the car 1 times velocity of the car 1 plus mass of the car 2 plus velocity of the second car, and that is the initial momentum of the system. And the final momentum is total mass, because they stick together. Mass is m1 plus m2 and the final velocity is vf. Therefore, by solving this equation and isolating the final velocity vf, we can find the final velocity of the system. And this final velocity is equal to the initial momentum divided by the total mass. Let's see some examples on inelastic collisions. A 1400 kilogram car moving at 3.2 meters per second speed is struck in the rear by a 2900 kilogram truck moving in the same direction at 5.30 meters per second. If the vehicles stick together after the collision, what is the speed immediately after colliding? Now the vehicles stick together and therefore the collision is completely inelastic. And we can find the final velocity value with the equations we derived in this slide. The final velocity is initial momentum of the system divided by total mass. Therefore, now we are given the mass of the car 1 and mass of the truck, and also the initial velocity of the car and the initial velocity of the truck. So let's substitute the numerical values to these equations. M1 is 1400 kilogram and initial velocity of car is 3.2 meters per second plus m2 is 2900 kilogram and velocity is 5.3 meters per second divided by the total mass, which is 1400 kilogram plus 2900 kilogram. Therefore, the final velocity is 4.6 meters per second. Now let's do another example. So this one says if the two railroad cars are of equal mass and one of is at rest before the collision. If the other car has an initial speed of v, what is the final speed of the two cars? That means there are two cars, both has equal of mass of m, and the second car is at rest, so the initial speed is 0, and the other car has an initial speed of v. Now we are asked to find the final speed of the two cars after the collision. Again we can use the previous equation for final velocity, and now we are given the mass of the two cars are equal, therefore m1 equals m2 equals m, and the initial velocity of the first car is m, then the second car is 0. Therefore this value goes to 0, and Vf is m1 v1I over m1 plus m2, because this term is 0 as the initial velocity of the second car is 0. Now m1 is simply m, vi is v, m1 is m, and m2 is again m. Therefore it is mv over 2m, and m get cancels, therefore it is v over 2. Therefore the final speed is 1/2 of the initial speed. Now let's see a conceptual example involving kinetic energy. A railroad car of mass m and speed v collides with and sticks to an identical railroad car that is initially at rest. After the collision, is the kinetic energy of the system half, 1/3 or 1/4 of its initial kinetic energy. Now we have a railroad car of mass m and speed v, and it sticks to an identical railroad car, that means mass is m, but it is initially at rest. Now after the collision, we are asked to find the kinetic energy of the system. Now before the collision, the kinetic energy of the system is Ki, which is half mv square, because there is no kinetic energy in the second car because its initial speed is 0. Now what about the final kinetic energy? So after the collision, both sticks together, therefore final kinetic energy is after the collision they are both sticks together, therefore mass is 2m, and it has a velocity v. And previously we found in this type of collision velocity is v over 2. Therefore final kinetic energy is half, mass is 2m, and velocity is v over 2 square. And by solving this, 2 cancel, and it is mv square over 4, and this is equal to half mv square, and this is the kinetic energy, initial kinetic energy. Therefore it is half of the initial kinetic energy. Therefore we can say that 1/2 of the initial kinetic energy is converted to other forms of energy after the collision. So in the collision of railroad cars, no momentum is lost, but some of the initial kinetic energy is converted to other forms. Some can propagate away as sound, and some is converted to heat, and some creates permanent deformations in the metal of the latching mechanism. Therefore the answer is A. Now let's see one more example. On a touchdown attempt, a 95 kilogram running back runs towards the end zone at 3.75 meters per second. And a 111 kilogram linebacker moving at 4.10 meters per second meets the runner in the head-on collision. And if the two players stick together, what is their velocity immediately after the collision, and what are the initial and final kinetic energies of the system? So now in our sketch, we let subscript 1, which is referred to the person in the red and grey, running back, who carries the ball, and the subscript 2 refers to the blue and gold linebacker who makes the tackle. Now the direction of the running back's initial motion is taken to be in the positive x direction. Therefore, the initial velocity of the players, for the player 1 it is 3.75 meters per second and it is in the positive x direction. But for player 2 it is in the negative x direction, therefore velocity is negative value. And we can find the final velocity by applying momentum conservation to the system. So initially the players have momentum in opposite direction, but after the collision they move together with the combined mass of m1 plus m2, and let's say the final velocity is vf. Now in part B we can find the kinetic energies by applying half mv square to the players individually to obtain the initial kinetic energy and to their combined motion for the final kinetic energy. Now let's do the calculations. So we are given the mass of the player 1 and velocity of player 1, and also the mass of player 2 and the velocity of player 2, and we are asked to find the final velocity and the initial and final kinetic energy of the system. First we can apply the momentum conservation because we know m1 v1, m2 v2, and we know the combined mass after the collision. Therefore we can find the final velocity using momentum conservation. So in momentum conservation, initial momentum of the system is momentum of the player 1 m1 v1 plus momentum of the player 2 m2 v2, and the final momentum of the system is m1 plus m2 times vf because after the collision they both stick together. Now we can find the final velocity from this equation. Vf equals m1 v1 plus m2 v2 over m1 plus m2. Now we are given the m1 value, v1, m2 and v2. Therefore we can substitute those values to find the final velocity. And if we substitute the values, we get vf is in negative x direction. That means after the collision both are moving in the negative x direction. Now in part B we have to find the initial and final kinetic energies of the system. So initial kinetic energy of the two players is half m1 v1 square plus half m2 v2 square. Again we know m1 is 95 kilogram, v1 is 3.75 meters per second, and m2 is 111 kilogram and v2 is 4.10 meters per second, but it is a negative value. Therefore we can find the initial kinetic energy as 1600 joules. And the final kinetic energy of the two players, it is half m1 plus m2 times vf square. Again we know m1 and m2 and we found the vf in part A. So by substituting we can get the final kinetic energy of the system, which is 23.7 joules. So it is way less than the initial kinetic energy. Therefore we can say that after the collision the two players are moving in the negative x direction. That means away from the end zone with a speed of 0.480 meters per second, and this is because the linebacker has more negative momentum than the running back had positive momentum. Let's see another example before moving into the two-dimensional collisions. So in a ballistic pendulum, an object of mass m is fired with an initial speed vi at the bob of a pendulum, and the bob has a mass of capital M and which is suspended by a rod of negligible mass. And after the collision, the object and the bob stick together and swing through an arc, eventually gaining a height h. Now we are asked to find the height h in terms of m and vi and the gravity g. So now our sketch shows the physical setup of the ballistic pendulum. Initially only the object of mass m is moving, and it moves in the positive x direction with a speed of vi. And immediately after the collision, the bob and the objects move together with a new speed of vf, which we are going to determine by the momentum conservation. Finally, the pendulum continues to swing to the right until its speed decreases to 0, and it comes to rest at the height of h. Now in this case, there are two different physical processes happens. The first one is the collision between the bob and the object, which is completely inelastic as they stick together after the collision. But since the collision is inelastic, kinetic energy is not conserved in the system. Next, after the collision, the remaining kinetic energy is converted to gravitational potential energy, which determines how high the bob and object will rise. Now let's do the calculations. We are given the mass of the object m and mass of the bob, and also the initial speed of the object, which is vi, and we are asked to find the height after the collision h. So now our first point is to apply momentum conservation. So initially only the object is moving, therefore initial momentum is simply m times vi. But after the collisions, both stick together and move with the velocity of vf, therefore it is m plus m times vf. Therefore from this equation we can find the final velocity of the system, which is m over m plus m times vi. Now we can find the kinetic energy of the system just after the collision. So that means at this position the kinetic energy is half mass is the total combined mass m plus m, and velocity is vf square, and we can substitute the vf from here to this equation, which is vf is m over m plus m square vi square, and by solving we get half m vi square times m over m plus m. Now we know the final kinetic energy after the collision, and this should be equal to the gravitational potential energy of the bob and object combination at the height h. Therefore we can equate the final kinetic energy to the gravitational potential energy. So it is m plus m gh. Now we can find h by isolating h in this equation. Therefore the height after collision is m over m plus m square times vi square over 2g. That is the height after the collision. Now let's consider collisions in two dimensions, where we must conserve the momentum component by component. So to do this, we set up a coordinate system and resolve the initial momentum into x and y components. Next, the final momentum should have the same x and y components as the initial momentum. That means the x component of the momentum should be conserved and the y component of the momentum should be conserved. Therefore, in two dimensions, if there is no external force acting on the system, we can say that the momentum should be conserved in each direction. Let's do an example to show how to solve problems in two dimensions. A car with a mass of 950 kilogram and a speed of 16 meters per second approaches an intersection, as in this sketch. And a minivan, a 1300 kilogram mass, which is traveling at 21 meters per second, is heading for the same intersection, and the car and the minivan collide and stick together. Now we asked to find the direction and the speed of the wrecked vehicles just after the collision, assuming external forces can be ignored. Now in our sketch, we align the x and y axes with the crossing streets. Therefore, with this choice, the car's initial velocity is in the positive x direction and the minivan's initial velocity is in the positive y direction. And let's say after the collision, the two vehicles move together as one unit with a speed of Vf and a direction angle theta with respect to the positive x-axis. Since we can ignore the external forces, we can say that the momentum of the system is conserved during the collision. Therefore, x component of the momentum should be conserved and the y component of the momentum is conserved. So these two conditions determine the two unknowns, the final speed and the final direction. Okay, now let's do the calculation. So we are given the mass of the car and the initial velocity of the car, whereas the mass of the minivan and the initial velocity of the minivan, and we are to find the final speed and the final direction. Now we can apply momentum conservation in each direction, x and y direction separately. So momentum conservation in x direction is car is moving in x direction, therefore it is m1 v1, but car 2 is moving in y direction, therefore it doesn't have any x component, but after the collision they stick together, therefore combined mass is m1 and m2, and they are moving in an angle theta respect to the x-axis, therefore it is Vf cos theta, because if we say this is the final velocity Vf and angle theta, x component is Vf cos theta and y component is Vf sin theta. Since we consider the x direction for this equation, we take Vf cos theta. Now the momentum in y direction. So for the initial momentum, mass 2, which is the minivan, is moving in y direction, therefore initial momentum is m2 v2, and since the car is moving in x direction, there is no component in the y direction for the car. But after the collision, both are moving in an angle theta. Because of that, the y component of the final velocity is Vf sin theta. So we number the first equation as 1 and the second equation as equation 2. And we can divide equation 2 by equation 1 to find the angle theta. So if we divide 2 by 1, we get m2 v2 over m1 v1 equals to m1 plus m2 Vf sin theta over m1 plus m2 Vf cos theta. So here m1 plus m2 cancels out and Vf cancels out, we get tan theta. Therefore we can find the angle theta. Theta is tan inverse m2 v2 over m1 v1. Now we know the values for m1 v1 and m2 v2, therefore we can find the angle. So let's substitute the numerical values. Theta is equal to tan inverse m2 v2 over m1 v1. Now let's substitute the numerical values. Tan inverse m2 is 1300 kilograms V2 is 21 meters per second and M1 is 950 kilogram and V1 is 16 meters per second. Therefore, theta is tan inverse 1.8, which is 61 degree. Now we can find the speed by substituting theta in the equation 1. Equation 1 is m1 v1 is equal to m1 plus m2 vf cos theta. Therefore, vf is m1 v1 over m1 plus m2 cos theta. And if we substitute the numerical values, m1 is 950 kilograms, v1 is 16 meters per second and m1 is 950 kilogram plus m2 is 1300 kilogram times cosine angle is 61 degree. So if we solve this, we get 14 meters per second as the final speed. Now that's the end of section 5 in this chapter, which is about inelastic collisions. So far we learned in an inelastic collision, the final kinetic energy of a system is not equal to the initial kinetic energy of the system for inelastic collision. And in a completely inelastic collisions, the objects hit and stick together after the collision. And finally, in two-dimensional collisions, momentum conservation must be applied to both x and y directions separately. Now let's move to the next section, which is elastic collision.